Oh, that works. All right. So for VAEs that you left in the middle, you're going to follow up on that this Wednesday. So for now, we're going to take a little advance forwards further, and we'll start the reinforcement learning section. I don't know how many of you are familiar with reinforcement learning or just with the idea of it. Well, if you are very familiar, you may waste your time here, but yeah, you never know. So reinforcement learning is its own field, and there is a very large intersection with deep learning, and we're going to focus a lot on that, but mostly starting next week. And for now, we're going to study RL itself. So basically, today there will be no deep learning at all. That should change a little bit for you. This curve represents how Big SHA expects you to understand the course as a function of time. Starting at slide 10, it's supposed to become difficult. I think it's mostly a question of like adding new concepts and notations. So just try to follow up, keep up, and it should be all right. Because the ideas in their sense are very simple. It's just that there is a bunch of new concepts coming at once. All right, so we start with this little example. So that's the kind of situations where RL will eventually come in handy, but we'll start in the simplest way possible. So you've got a spider named Flider, and you've got a fly named Spy. It's very easy to pronounce. So Flider is at the far corner of this room. The fly is at another corner, and the spider, he wants to catch the fly. So for that, it can walk on the edges. It chooses the edge that it walks on at random. To cover the distance of one edge, it takes 1 minute. And when you arrive at the end of an edge, you randomly choose another one, and you repeat that. You can also come back if you want. So question for you. What's the life expectancy of the fly? That's an actual question, so you can try to guess. It's a little probability exercise. No? It's going to be very interactive today. So because anyway, the quiz is filled with questions like that, so you might as well start working on them now.
So where would you even begin to answer this question?
No?
Actually, let's try this. There are 7 people in class. So let's go around and ask each of them how you would begin answering this question. Let's try that. What would you do? So how do you even start formulating this?
Just rewriting the rules here.
Right? No clue? Okay. What about you? How do you formulate it?
No. Okay, let's just give a little hint.
So, okay, hang on. Maybe this will help motivate you. This is a question that frequently came up in Goldman Sachs interviews. Okay, so you're really, this is not just something you're doing in a classroom. This is for like a $200,000 figure job. And you have to answer this, and you get the job, and you don't think more.
Sorry?
So how do you get to the answer?
Just like if the spider and the fly both move to D3, then the fly dies. So it takes only one step.
You can assume the fly doesn't move for now.
The fly is not moving. The fly is static.
Oh, the fly's not moving? No.
Yeah, it's just the spider.
Okay.
I don't know, by the way, if we are hearing people talking when it's online, but for the people that are watching, it might become boring.
Exactly. Let me get on here.
So it's 1 minute per edge, right?
Yeah.
And then it's a random
Yeah.
So it's probably just a few minutes, right? Just a couple minutes. I mean, it's random if it gets to T2, so it can be going to the flag.
Probably a few minutes is.
I mean, I don't know.
Yeah.
If you can't.
Well, if you
3 minutes is my expectation.
you think about it, if you think about it, here you start at T1. Let's imagine you started at T8. What would the expectancy be in this case?
0.
0. This one is easy. Well, T is the time actually. So if you start at 8, the time T8 is 0. If you start at corner 3, what would it be?
Well, you have for 50% chance of it going to T8 from there, and a 50% chance of going to T5. And if it goes down T5, you have to think about if it goes down to T4, T7.
We forgot T1.
Oh yeah, T1 as well.
So it's 1/3, 1/3, 1/3 actually.
Yeah, you have to like calculate all the possible ways it can get it.
Yeah.
To do an average, right?
So if you write it down, T3, it's going to be, so you said in one case out of 3, you're going to directly to the fly. So in that case, the time is
2.
1 minute.
1 actually.
1 to T3 and then 1.
So what about
And-
this 1 minute to traverse the edge?
Right. That's
We're assuming you're starting on 3 right now. That's the assumption. So 1/3 T8. So this one is 0. So if you go on T5 instead, so you don't know the time in T5, but you can still know the relation. So in that case, you got, in one case after 3, it's going to be 1 plus T5. And finally, one case out of 3, 1 plus T1. So that much you can do for any of the corners, and you get 8 equations. One being T8 equals 0. So that becomes a system of linear equations that's perfectly solvable at this point. So once you'd be there, it becomes easy. We're not going to finish and find the actual expectation today. But if you were arriving at that point, you could do it. So that's just like a short introduction. But basically, the idea is that if you write it down that way, it becomes easy. Let's imagine if it's not a cube, it's a dodecahedron, I think. Fuller's dome. Well, how would you do it in this case?
How is it any different from the cube?
It's the same thing.
It's the same thing. Thank you. Just to say, it may look harder, but it's actually kind of the same thing. And you can imagine that if you were, instead of being a spider trying to catch a fly, but you were a chess player trying to move around the board of all possible chess combinations, roughly be, you could arrive to the same reasoning. It's just that there is many more nodes in this graph. So we're switching gears a little bit. Reinforcement learning, it's a section of machine learning that enables you to solve situations kind of like that, where basically you've got an objective and you have or like a goal, and you want to reach that goal, but you don't know how. You're kind of like exploring the situation. Learning how to play chess, you do that by reinforcement learning. It started, by the way, it's you've probably heard of Deep Blue, I assume, one of the first supercomputers. Maybe you know that it started here in CMU. with the name Deep Thought 10 years before that. Now, if we were to ask you how to write a program that beats champions at chess, you may think I can just write a table of all the rules that make for a good strategy, but that's actually, it's more intractable. It's like super intractable. There are just the number of possible positions would amount to more than the number of atoms in the universe. So it's a little hard. And even if you were to simplify that in in terms of general principles of I want pieces to be in the center and stuff, even there you'll have a lot of trouble because again there is a lot of them and it's not like there is a book of all the general principles and you just have to follow it to beat a champion. So you couldn't solve that without a form of automatic learning from the machine. The question is, how would you actually do it? If you think of how humans do it, you learn by playing, because you've got a memory and you remember what you did. Part of it is reflexes and just subconsciously remembering what happened, and part of it is actually memory and you totally remember what happened in which parties, in which games. It looks like the greatest champions have a super large memory of the games they played, and it helps a lot. But then again, if you just learn a list of possible games, you'll never get over all possible board positions, because there again you'll see a fraction of it that amounts basically to 0. So you're gonna need definitely a way to generalize knowledge to more games. But the question, what does generalizing mean in this kind of context, is actually a little hard to grasp. But you can get a little idea of it. So we're gonna start by doing that today in a little abstract way. Let's say you've got a diagram like this of we're gonna say that these are chess positions. Each of the nodes is a position, and you've got some edges between nodes to say with one move I can go from there to there. I'm not representing the edges here, but you can get the idea. There is a lot of them, really a lot. And in the beginning, you have no idea whether there are good positions for you or bad positions. So let's say you're playing games, a very, very large number of them. Some of them you're going to win. And every time you win a game, you're going to give a little green color to all the board positions that you used during the game. And every time you lose, you give it a little red color. So let's say you won. It would something like that. We're only coloring the nodes that you played, so it's 1 out of 2. The other one is your opponent. So that's just to say these are good board positions, and you want to remember that. But you're not going to use the same green for all of them, because the last ones, you're pretty sure they are the ones that led you to the final outcome, which is winning. But the more you go into the past, the more unpredictable the future is from that point. And so you can't be completely sure that the first or the second positions are played a significant role in winning. So you're gonna make them green, but a little less, and you'll get gradation of green colors for these board positions. For this, let's say you do the same thing for the games that you lost, and at the end of the day, you've got something like that for a lot of games, like really a lot. Some of which you lose, some of which you win, and sometimes some positions appeared in both winning and losing games, so they're going to be somewhere in the middle with a yellowish color. That mostly happens in the early stages, obviously. That's like the same thing as what I was talking about before. Like in the beginning, a position is like far away that you don't really know yet if it's going to lead to a victory or to win or a loss, but in the end, it's more likely to figure out the outcome. You can play even more games by playing with yourself. You can actually, when I said you are playing games, you can actually play games with the machine and an opponent, but that would be slow. You can learn by reading games in books, or you can play with yourself. Everything's possible. That's how like AlphaGo 0 works, playing with itself, for example. So in the end, you get big diagrams of winnings and losing in the in shades of green and of red and of yellow. And then you've got all the nodes that you didn't go through, which again, because there are so many possible nodes, are the vast majority of them. So how do you add a color to these nodes? That's like one of the biggest questions of reinforcement learning is that. So you're gonna need a kind of magic, as we say. So like a function that's gonna assign colors to board positions based on the games that you play. So that's the part where, like spoiler alert, like where deep learning is gonna come in handy eventually. But this part of RL you're gonna focus on much later in the course, and today we are gonna focus on another question, which is from a position, where do you move? We're assuming that we actually know, we have seen all the positions in the game, and you've got the shade of green and red for each of them. So it's probably not chess, it's like a much simpler game. But even if in this situation, that's not telling you at all what the next move should be for you, the player. So from the black circle, what's the good position? So you've got a bunch of possible moves. And if you were, for example, to go to the greenest available node, that would probably not be a good choice. It's like the greedy choice, but it's highly unlikely that this is the best choice that you can make if you want to win. So where you actually want to go is to do the move that is going to give your opponent the smallest chance to win. But how would you actually know that? Well, that's kind of the question. Fortunately, you can make some simplification assumptions. So for all this lecture and for all reinforcement learning in general, to make things simpler, you assume that you're in a Markov process. So you're probably already at least a little bit familiar with that idea. Markov process means that the past doesn't matter. Only matters the present situation of where you are for all the future decisions that you're going to make. Which, for a chess game, for example, makes total sense. But you'll once you know the board position, you should be able to figure out the best strategy, no matter what happened before. We're going to go back on that a lot today, but it applies to basically everything, not just to chess. So the question we're asking today is how to figure out if a move is good based on all this experience that you have added up. Usually, the biggest challenge is that you don't know if a move was good until you finish the game. So that's true for chess. It would be true for a bunch of situations, like if you're investing on the stock market, you buy Apple stocks in the 90s, and it looks like it was a terrible decision, and 20 years later it was the best decision of your life, but it took that long to figure it out. If you are driving, you want to change lane, which one is gonna add up to you arriving at your destination the fastest? So in this case, you kind of have a sort of immediate assessment of if it was good or not, because you see if you're going faster or not. But again, in you don't know if it's gonna pay off in the 10 minutes later or not. So all of these are, to formalize it a little bit, they are reward-based problems. So the actions that you do, they beget rewards. Possibly, first of all, these rewards are not deterministic, so the world isn't completely predictable. You just have some tendencies of this action is likely to give some good results, good rewards, but it may also happen in a different way. If you're same thing with chess, if you're depending on the opponent that you're playing against, one move may result in even from the same board position, a move may result in different outcomes. So from these rewards, you're supposed to learn to act rationally. We keep formalizing. You've got this is a cartoon of the world, so there's you. You are called the agent. And there is the universe, which we're going to call the environment. So that's, if you're playing a game, it's going to be the game. If you're buying stocks, it's going to be the market. If you're driving, it's the road, etc. You are taking actions. The actions affect the environment. And the environment then is going to change based on your actions and some unknown factors that you are modelizing with a probability distribution. But basically, they are you consider they are deterministically speaking, they are unpredictable. The environment is affecting your own situation by emitting a reward, positive or negative. But then again, that may take a very long time, and at first you don't have the relevant reward yet. Your question is, how must you, the agent, act to maximize the rewards? So if you're looking at this from the environment's perspective, you've got actions coming in, and you change in response to those actions, and you return a reward, or reward is a general term. It can be negative, in which case it's a punishment, but you always call that a reward, to the agent. From the agent's perspective, you are taking actions, and you are seeing observations of the environment and the reward that you got. So that's your basically, we can call that the agent's world if you want. And again, the agent's objective is to maximize the rewards. We're repeating a lot so that it becomes clear, but because there are going to be much more terms than rewards and observation, we hope that all are going to be clear. If they are not, or something you forgot, or you're confusing two terms, raise your hand. So, we keep formalizing. These problems, in general, we're calling that reinforcement learning because you are perceiving a reward signal and you want to reinforce it, which is make the positive reward stronger in the future. The big difference between that and supervised learning that you are mostly used to is that there is no one telling you you did well at this specific moment. You just have the reward that's possibly delayed, and also you don't have the golden target to compare with. Like you don't have good moves at your disposal usually. The reward is going to be a scalar, single number, sometimes negative, sometimes positive, depending on if you win or if you lose. It can be delayed. And the agent wants to optimize its actions to maximize the reward. So if you want to maximize the reward, we're going to represent the environment as a process, which is going to be a big math formalism with probabilities and stuff that we're going to spend the rest of the lecture defining, and we are probably not going to be done by the end of the lecture, and you'll have to finish that next week. So it's a mathematical characterization with a true value for the parameters that represent the environment. In the agent's job, there is a big modelization component where you want to understand how the environment works so that you can maximize the effect of your own actions. So you're going to want to understand the environment by a way that's going to be as close to the actual truth as possible. But you can only do that from the part of the environment you observe, which is a big source of difficulties. And from that, you're supposed to formulate your winning strategy. So at every time t, you're going to make your observation of the environment, receive a reward, and perform an action. So the observation will be O, the rewards R, the actions A. Remember that. And from the environment's perspective, at each time you receive an action, you emit a reward, and you produce a new observation O, t plus 1. So that's the part you are interested in, mostly. The environment is modelized by something else. So from the agent's perspective, things happen this way. First observation, then reward, then action, then observation, then reward, then action, etc. And the history is going to be the sequence of all of those. And you're going to need to model this sequence so that you can choose the best action t at every time step. But the strategy, the good strategy is the one that maximizes the sum of all of the rewards. So you see, like in the situation that we talked before where you only know the outcome at the very end, then all of the first rewards will probably be 0, and only the last one is going to be high. That doesn't necessarily have to be the case. Sometimes it will be. From the environment's perspective, you're going to modelize that with states. So a state is going to be like the relevant summary of the observation. So it's a value that's going to be supposed to capture the relevant status of the system. Like if you're in an automobile, all the characteristics like position and speed, acceleration are going to be useful. In chess, it's going to be the chess of the board and whose turn it is. Like the hour that it is in the afternoon is not relevant, but this is relevant. So you just that's the relevant status. That's how you should think about it. The state which is what is eventually going to decide the rewards, might be very complex. You assume that it's dynamic and that the agent's action can affect the way that it responds in response. But there is an important distinction that you have to make between like the true state and the state that you're using. The true state you probably cannot observe it all, but you're still going to use a state in your model. So it's not a big deal if you can't observe all of it, as long as you've got the Markov property, which you're going to want. Again, a well-defined state captures all information that you need to predict the future. It's the same thing as what we did before. The past shouldn't matter, only the present should matter. So formalized, it means that the probability of the next state based on all the history is only the probability of the next state based on the current state. But hopefully you're all already very familiar with that. Now, we're going to still make a little example to check how familiar you are. So back to the spider that you're going to see a lot today. So this time we're not interested in Flider, but in its brother glider that is pretty much doing the same thing. It also wants the to catch a fly. That's not represented here, but whatever. The big difference between glider and Flider is that glider doesn't turn around. Like if you went to a state from a direction, you're not gonna go back in the same direction at the next step. So my question for you is glider Markovian or not? I see a no here. Who's voting no?
Take a vote. How many of you think glider is a Markov process?
Is it a question or are you voting?
I mean,
You're voting?
You have to take you have to decide one way or the other. So
Yeah.
how many of you think?
Bonus point on the quiz. Joke.
So the rest of you think he's Markovian? Stephen, is he Markov or not? No? Okay.
Okay.
And you?
I think that depends on your previous state. So if your state is only the previous position, then it's not Markovian. But if you define the state to be like a two-dimensional vector, I think it's possible to define this.
Good call. That was the good answer. So the apparent state, the one that seems to make sense when you look at this, like from your chair, is to have one state for each corner. Here, it's not a good choice for your states, precisely like you said, because if that's your state, then glider is not Markovian. So if it's not Markovian, then you cannot do anything with it, and all the reinforcement learning system is going to crash. So you're going to pick a different definition for your state. You could say that the state is actually the history of all the previous positions. That's a little complicated. You can just say that the state is the two previous positions, and then the problem is Markovian. Is that clear for everyone?
So if you just define the state as the edge with the direction, so each edge becomes two states, going from left to right to left. And this one is going to have 12 times 2, 24 states. And then the process becomes Markovian.
Yeah. So we've got a little more states, a bit more states, but it pays off because now it's Markovian. You see why 24? Because for like you have got 8 corners, but for each you can come from 3 different positions. So it's 8 times 3. If you were to pick 2 states in history, it would become 72. So the Markov property, it is true for the supposedly ground truth of the environment that we assume exists somewhere. Because like I think it's a safe bet to say that the laws of the universe are such that if you got the entirety of the present, you probably can predict the future, except maybe some tricky quantic phenomenon, but we can just ignore that. But that doesn't mean that the state that you use is always Markovian. That's a modelization choice that you have to make. But it's not like straightforward obvious. So ideally, the agent should know all about the state and its dynamics. Of course, in practice, you're not gonna know everything, but hopefully you know enough. So that's a previous slide. Again, the agent wants to model the environment process so that it helps devise strategies. So
There's a little bit of definition that's kind of involved over here. So if you go back to the glider example, there's the apparent state, and then there's what we call the Markov state, which is often called the information state. So if you go by the information state, then we can define the process as being Markovian in terms of the information state. Right?
You always can.
You always can.
And you have to do it.
Unless if there's an infinite dependence, at which point things break down. Now, over here, there are two issues that we want to come up with. One is that if you think of the environment as Markov, the environment has its own actual Markov states and its own dynamics. Then there's the second one, which is the agent's model of the environment, which is not perfect. And so the agent is going to operate based on how the agent thinks the environment behaves. The environment is going to behave according to how it really behaves. And you have the dichotomy between the two. And you're looking at the world entirely from the agent's perspective, keeping in mind that the universe is minding its own business.
Pretty much. All right. So again, you formalize. Formally, you've got an agent state that's a function of the history. And the closer that is to the true environment state, the better your model is going to be, and probably the better your strategies in terms of actions are going to become. Here's an additional example. So there is a rat. The rat is in a cage because scientists are monsters, and there are like observations. Like the rat sees, sometimes it sees like a light, sometimes it hears a bell, and its actions are to choose to or not to press that thing. How is it called?
The
Lever, like for alcohol. Okay. So in one case, you see the light twice. You press the lever and you hear the bell, and you get an electroshock. Second case, you hear the bell, you see the light once, you press the lever twice, and then you get some cheese. Now, the third case, you press the lever, you see the light, you press the lever again, and you hear the bell, and then what happens? You think how would you predict if it's what's coming is a shock or a piece of cheese? Think it's a shock? Why?
Well, because they're much similar than the cheese. The sequence I mean. The sequences look more alike the first one because the last three of them are exactly the same. And
fair enough. So if, for example, you would assume that the state was light plus, like the state is you just heard a bell, for example, then it seems to be similar with the first one, and therefore most likely it's a shark that's going to come. But if what's relevant is the number of times you press the lever, then it's probably going to be cheese, right? So there's no answer here. The whole point of that example is to show you that the different definitions that you can give to a state are going to end up giving you different predictions of what's happening.
Again, this is to show the difference between the agent's definition of the state and the universe's definition of the state. There's a difference. And the agent can define the states in different ways. Different definitions are going to give you different outcomes.
So once we're going to start reinforcement learning, actually, we're always going to talk about the engine state and assume that it's the same thing as the environment state. But it's good to keep in mind that that's actually not the case. It's really a modelization choice, and it can be a good one or it can be a bad one. But that's the end for this principle. Just hope we're gonna remember it after that. Actually, is it the end? No, there is a little bit more on that. So we're follow up. The Markov property is something that is going to be valid if you properly define for a properly defined environment state. However, if you don't know the environment internally from the observation, you cannot decide that the model you're creating is Markovian. That seems very obvious. It's something people tend to forget. I don't know if you're familiar with hidden Markov models, but there's Markov in them, but they're actually not Markovian. Or more precisely, in this kind of model, you've got observations that are not Markovian at all, and you make the assumption that somewhere internally there is a state that is Markovian, and the observations are a function of that. But the observations aren't Markovian. So the environment, the observation that you see might be something a little bit like that. Now, in practice, you can assume anything. Your model is going to be local, but that doesn't you can still assume that the states behave in the Markovian way that the environment does. If they don't, well, too bad for you, I guess. But you've got to hope that they do, so that reinforcement learning can hold. Like for the chess example, it's fairly obvious that the environment state is Markovian, although you could argue that what's happening in the psychology of your opponent also holds some significance for what's happening, for what's gonna happen in the future, and that if you can manipulate them by a certain way of playing and affect their tendencies on the long term. But so the board may not be Markovian strictly speaking, but you can still assume that it is for all of the models that you're going to make, and that's how people do automatic chess players all the time. I don't think anyone's been trying to modelize the opponent's psychology in a chess game. Yeah.
What specifically is the state in this chess game? Is it a single move or all the positions?
No, a move is an action. A state would be the entirety of all the positions on the board and what chess piece is on each of them, like the entire board position plus whose turn it is to play. All of that is important. So all of that makes for the state. If you've got that and you assume that it is Markovian, you're not going to be too much wrong. And you can make a bunch of very good models that are going to beat world champion just with that.
So basically, the entire board, which is to say, it's a 64, you can think of it as a 64-dimensional vector, where each vector can take one of, each component can take one of 16 values, plus a sign which tells you who's going to be multiplying next.
But back into the example, the rat example, then in that example, what is exactly the state is? Is that a single
here,
bell?
okay, the point is we're only showing you the last 4 bits, right? So you could define the state in different ways over here. So you could define the state as just the last event that happened, in which case the state is going to take one of 3 values. Or you could define the state as, the number of times the light bulb went on. So there are different ways of defining the state. In the case of the chess board, the definition that makes most sense is the status of the board and who's going to play next. Because that pretty much decides what's going to happen afterwards, right?
So to finish that part, if you observe the entirety of the environment states, then the states that you're going to make with those observations are going to be Markovian, and you're in a Markov decision process. But if you're only observing a subjective part of it, then you maybe end up in a partially observable Markov decision process, but that's way too hard, and we're only going to do the first one. Now, again, this is the Markov property, and you can define your states so that they have that property. I think it's okay with the principle, so we can move on a little bit now. So now we are going to create a formalism, and we are going to gradually increase it to end up with something we can do learning on. So Markov process is a random process where the future is determined by the present. If you formalize it, what you need is a set of states that you're calling S, capital S, and you've got transitions probabilities from one state to the other. So if you've got a finite state S, which for example for chessboard it's the case, it's very large but it's finite, then the probabilities can be formalized as a transition matrix, which is a stochastic matrix. We have a lot of hand properties that are going to come in handy later. Now we're going to note P of S condition on S prime by, that means the probability of the state at some time t plus 1 equals S is the probability, conditions on the state at the previous time step was S prime. And again, that because you're in the Markovian assumption, that's the same for any time t. Though the time doesn't matter, and that's why we can make this shortcut. And therefore, we can just call it P S prime. So again, the transition probability in the finite case is a matrix. And if you're in not in a finite state, or if you're in a too large state, or just even a continuous one, you're usually going to use a kind of model of so the probability is going to end up being a function of the states and some parameters. And learning these parameters is going to be a big deal. But that's for a later lecture again, when we're going to do deep learning with that. For now, the transition probabilities are going to be finite. So in the spider case, so this time it can go in all directions, it's Flider. What would the transition probability matrix be? That's a question. That's the example we saw at the very beginning. So it should be relatively similar to that. Okay, I'm following your instructions and I'm writing it on the board.
Michael, what is the probability? Let's first assign some numbers to the states. How many of them are there? 8, right? Okay. So let's call the corner in which the spider is. So Rafan, can you actually put some numbers on the states?
Oh yeah, we don't have the numbers anymore.
Just put them arbitrarily.
Yeah, it may be not very large. Can you see and or guess the numbers? Okay, 1, 2, 3, 4. Better? All right. Your turn. What do I write here? Sorry?
2 1 is 1 over 3.
1, 1 is 1 over 3?
2,
2, 1. So 2, 1. Yeah. 2, 3. And in the middle? 2, 2? 0. Thank you. And is here. 2, 4? 0. Thank you. And there? Also 0. Thank you. Yeah, I think you get the idea. So, the first line, just to finish.
Maybe ask Michael to fill out the first line.
Yeah? Okay. Michael, first line.
Well, I don't get what exactly it means 1, 1 here, because the spider is currently stand at the point of 2, right?
Yeah, but like on the drawing it is, but it could also stand on the 1. Assume it is on 1. What happens then?
Well, then all the adjacent edges would be 1/3. Would be signed as 1/3.
Which means
Will be 1, 1 will be 0, and 1, 2 is 1/3. 1, 4 is also 1/3. 1, 8 is also with the probability 1/3, and the rest would be 0.
okay. Well, you got it. I think we can spare you the next 6 lines. So, now the spider doesn't want to turn back. Again, I think we asked you that before. Is it a Markov process? Yes, but with how many states? 24. Yeah, I think writing a 24 matrix would take more than the board, so again, we can spare you that, but it would be a little bigger to write, but you'd have 2 probabilities with 1/2 on each line. So, increasing this formalism a little bit, now we're going to do Markov reward processes. So, it's a Markov process, but on top of what we already said, at each step, each state is going to give you a reward. So when you arrive at a state, you obtain a reward that's drawn from a certain distribution, because again, the reward are not deterministic. Yeah.
So is that just what we've talked about, except we're guaranteeing the reward's not delayed?
We're not guaranteeing the rewards are delayed. We're in the formalism, the rewards can not be delayed, but even if you're formalizing a chess game with that, you would still have a reward at each time step, except sometimes it's going to be, most of the time it's going to be 0, and when you won, it's going to be 1. But the formalism is more general than the particular cases. Right, so now it's going to become a little bit harder to track. Here, the spider moves again randomly, but you've got flies at every corner, and the spider is catching a fly, trying to catch a fly, but because they are all of different sizes and some of them are harder to catch than others, you're not sure that you're going to catch one, but you're trying. So the reward in this case, which is 1 if you catch a fly, like if you get 0 if you don't catch a fly, and if you catch a fly, you get some reward that depends on the size of the fly, basically, because you get more to it. So in this case, that's just to show that the rewards can be probabilistic. They are corner-specific and probabilistic. So that's why when you formalize it, it's a probability of reward conditioned on the states where you're at. Is that clear? Yeah.
What if the transition matrix is stochastic? In that case, how can you make the matrix of that one? I mean, if you want to go to the last.
So define a stochastic transition matrix.
Yeah.
What do you mean by stochastic transition?
So I mean, when I want to go to last, but if it's a freeze state, so that I have a possibility to go to the one.
But you always have a possibility to go right. So I mean, it's a stochastic process, right? When you're speaking of a stochastic transition matrix, it means that you're actually changing the transition matrix randomly. That's a different level of stochasticity you're speaking.
We're going to add the complete formalism for that, so maybe it's going to be a little clearer in a couple of slides. So this, so that's the initial case with the spider, one fly, it goes every direction. Is it a Markov reward process?
What do you think this is a Markov reward process? Is the spider getting a reward at any point?
Yes, and what is the reward?
So there's a reward of 1 at one corner and 0 at 7.
Yeah. So one of the corner has a reward of 1, and all the others have a reward of 0. This time it's deterministic. So the probability is like the probability of 0 on corner 2 is going to be 1, and all the probability of 1 is going to be 0, and on corner 4 it's the opposite. So now we formalize that. So you've got your set of we're going to say finite states. You got the probability, the transition probability matrix PSS prime, and you've got a reward function, which we can say like reward distribution. So that's the probability of the different rewards conditions on the states. So I guess if you've got only a finite set of reward, that will also be a matrix, but it may you may also have the rewards being like a Gaussian function of the state, everything possible. So you can consider that, or you could consider, which we will do later, the expected value of the reward on the state. And you've got a discount factor that you haven't seen before, and you're all wondering what it is. So we're going to show why this can be useful. So if your reward is so your expected reward for the state that where you're going starting in 1, do you think the reward is going to be higher in 2 or higher in 3? Will it be 2 or will it be 3? Probably 2 here if you're looking just at the rewards, yeah, because there is seems to be like a bunch of flies over there. But that doesn't mean that's what you should do, right? So first of all, of course, you should make the distinction between the expected reward and the sample reward, because if I'm asking you which reward is going to be higher in 2 or 3, well, technically you cannot answer because you don't know, because that's going to depend on what's on the actual situation, and you're drawing that from a probability. But if we're talking about expected rewards, then you can say, yeah, the expectation is probably higher in 2 than in 3. However, does this mean that you should go in 2? Probably not, actually, because the choice that you should make, it's going to be not it should be driven not by the reward that you get, but by the sum of all possible rewards, if you remember. So which is the better choice in terms of expected sum of all the rewards you're going to get in the future, do you think? Should you go on 2 or should you go on 3?
Is there any constraints here?
Right now there isn't, no.
The highest reward would be going in a dead loop from the 1 to A5 and just keep going, so the reward will go infinite.
You're on the right track, but so
But
if you
put it this way, right? You can get to 4 in 2 steps if you go to 3, and then just stay at 4 forever, right? If you're going to 2,
for
I think that reward will be taken at this position and will be reproduced such a reward when you visit it the next time.
because the point is, think of the sum all the way to infinity, right? No matter how you slice it, if you get to 3 first, then you have a much bigger, once you get to 4 and you decide to stay at 4, it doesn't matter. So all that matters is what is the shortest path to 4 over there,
Okay.
2 or 3,
Then 3
right?
first.
because 3 is closer to 4, basically. Like from 3 you can go to 4 faster, and 4 is the best.
One-third chance of getting to 4. If you go to 2, the probability of
Yeah, it will wander wrong.
so
We cannot compare the results.
What did you say?
he says there's no discount factor,
Fair enough.
but
Yeah, that's precisely where we're introducing the discount factor, is that it seems obvious by looking at this that 3 is a better choice because it enables you to go to 4 faster. But from what we've said from now, you cannot formalize that. Why? Because if you sum the rewards at all time step, expected rewards, it's always going to add up to infinity, whatever you do.
question, right?
So yeah, you've got the right point.
But to answer your question, if you think about it in terms of discount factor, what is the smallest discount factor you're going to get at 4? That's going to depend on the length of the path. So if you take 2 steps back to 4 and then stay there forever, the discount factor is only square. If you take 10 steps, the discount factor by the time you get to 4 is 8.
So yeah. So
it's really the shortest path to 4.
So the discount factor, so this little gamma that is going to be between 0 and 1, that you're going to use to compute the return, or the discounted return. Return means the sum of all the rewards, and if you use a gamma like that in your sum, and you make, you're going to say then you have a discounted factor. And for time t plus k, you're discounting that by a factor gamma power k, and you're taking the sum of all of those. So this is useful for a bunch of reasons, but the reason that we've emphasized here is that it's going to encourage you to make the good decisions as fast as possible, because the return in that case is going to be higher if the high rewards are in smaller t. Which is usually a desirable property. So it's one of your choice when you pick a model to choose a relevant gamma factor. It has a bunch of other. It's useful for a bunch of other reasons that we may emphasize them later. But basically, in terms of interpretation, if you got gamma equals 0, then the return is just the current reward, and the future is assumed to be completely unpredictable. If you got gamma equal to 1, then the future is considered to be perfectly clear. So you just got to pay a little attention to the notation, because when you consider the return, you start counting the rewards at the time step right after that. So it makes sense when you're considering the reward from the state 0, but it's basically just a convention, but we're remember to use it. We're gonna apply that to an example to get familiar with the notion. So here you've got your spider that wanders, and it gets these flies at each time step. So we're in the example where there were flies everywhere. So this is what happens. First of all, are those sample or expected rewards? Question for you. There are so many people in the room today, so I'm sure someone has the answer.
So again, the spider actually went through the entire exercise and caught all of those flies on that one trip. So is that the expected reward for the spider, or was it the spider sampling the process? The spider was clearly sampling the process, right?
Yeah.
The sample rewards.
So we call those sample rewards.
For a small fly, big fly, small fly, small fly, big fly, small fly, small fly, and you ate too much and died. That's a sample.
So what would be the expected rewards? Well, if I just show you that, you cannot say. But if I'm asking you, under what condition would they be the same in terms of environment states and Markov process? Under what condition can you say that the sample rewards are the same as the expected rewards?
The size of the flies that are all the same.
No,
For yeah, that's one way of putting it. But in terms of Markov reward process, how would you formalize that?
if there's only one fly in each corner, each corner has fly with just one size. Then this is pretty much what is going to get every time. In which case, the expected and the sample reward.
Yeah.
So the distributions are delta.
Yeah. So in terms of formalism, yeah, it's when the rewards are deterministic, or if the probability distribution is a delta. It's the same thing. So let's compute the returns a little bit. So who can tell me what the return at time step t equals 1 is going to be, assuming the discount factor is 1? To make the count.
So again, the return is everything you get from here to infinity. The reward is what you get this number.
Wait, isn't the return everything from the step in front of you?
So
Yeah.
it's a question of how you define origin, right?
So what's your answer? I think I heard an answer at some point. 11.6
Summation of all.
from 2 to 9. Is that right? 2 to 9. Well, then it's good. Because I didn't make the count, but I assume it's good. At GT equals 7, Steven?
It's 3, right?
Yeah. Good. It's not that hard. So again, these are the same way that the rewards are sampled. Here, the returns are also sampled. With gamma 0.5 this time, you can just pick it for, let's do GT equals, at t equals 7, but to make it simpler, but with gamma 0.5. Sorry?
1.5.
No.
1.25.
1.25? No, neither.
Is it 1?
It's not 1 either. Yeah. Yeah. So yeah, it's equals 7. That's going to be 2.5 actually. By the way, I didn't. Yeah.
Why is that? Sorry.
Because the formula you're using is that of the discount factor, where for every time step in the future you discount the reward by gamma. So if I give you gamma equals 0.5.
Here you got to sort of distinguish between the concept and the implementation. Depending on which textbook you pick up, depending on how you're going to actually work this out, how you define the origin, how you define the discounts, may be shifted by a position of 1 and different ways of writing it. But the asymptotic behavior is the same in every case. So long as you're consistent within the arithmetic you're writing of the person.
Remember that example where you had the green and the red examples, but the earlier you were in the history, and the less green it should be. Well, that's pretty much what the discount factor is doing too. So we kind of formalize that as well. The discount factor is taking less account of the future, so because the reward is in the future, it's less green. It's the same. It's the exact same thing. Just a small parenthesis. Coming back. Wow, we've done so much stuff. Returns. Yeah, there we are. So the discounted return, it's a good objective. It's a good metric for what you want to have. But again, it's sampled, and therefore it's like depending on the actual process that you have seen, and what you are really interested in is the expectation of that. So what you want to maximize is the metric that you're going to be interested in is the expected return. This has a name, and we're going to give you the name very fast. So if the spider gets a reward of 1 when she gets the fly, it's got infinite patience, which means gamma equals 1. Then what's the value of what's the value of starting at each corner? Value meaning how good is it? Same. Yeah, the expected return, which is what you are interested in, it's going to be 1 for every corner, precisely, because you've got gamma 1, infinite patience. You don't care where you start. You're going to end up getting the spider. Yeah, so you can expect to get fly from anywhere. So this thing, the expected the expected return, because it's the it quantifies the value of each state, we're actually just going to call that the value function. So the value of a state is going to be the expected return as condition on you starting on that state. So that definition is highly important. So you can note that it actually doesn't depend on what time step you start counting from, again, because Markov property. But you can assume it's therefore you can assume it's at time step 0 that you're defining that, or you can just call it expectation of G condition on S, and everyone's going to understand. Slightly different example. So this is called we're going to call that the hungry spider. Now you don't have infinite patience. We're keeping the discount factor at 1, but this time we're assuming that every time the spider doesn't eat, it gets a negative reward of -1. Then, if you start at C1, what's the expected return?
So we're running out of time. So.
Oh, we are already? Damn. Well, we've done roughly half of this, so you can do the other half next week. And thank you for listening.
So I'll actually catch up with this on Wednesday and record a lecture on Friday. So.
Oh, you're going to do that? Okay, then you're going to catch up that Wednesday.
Yeah, this is fun stuff, guys. I mean, it's actually very